Hello friends, in this video we are going to discuss about the stability analysis of the BJT. So for that we have considered NPN transistor like this. This is the NPN transistor, this one, and the NPN transistor has been biased in this form where a RC resistance is connected at the collector and a RB resistance is connected at the base, and there is a voltage that we have connected at the base terminal is VBB, and there is a voltage connected at the collector terminal that is the VCC. So from this circuit we can say that this will be our input circuit. This is the input circuit and this one will be the output circuit. So we can say that right now the transistor has been connected in this format. If we apply KVL at the output circuit, then we will find that it will be minus of VCC plus ICRC, IC into RC, that is the drop across the RC, plus the collector to emitter voltage, that will be equals to 0. From this equation, if we find the value of VCC, it will be IC into RC plus VC. So from this equation, we can find that if we find the value of IC, it will look like minus of 1 by RC into VCE plus 1 by RC into VCC. So from this equation, this is the IC equation of the circuit. It is changing with respect to VC and VCC. So this circuit equation can give that it is similar to Y equals to mx plus C. This will be a straight line plot. If we plot the IC in the y-axis, so if I plot the IC in the y-axis and VCE in the x-axis, then we will get a plot like this. This will be a straight line plot because the slope here is negative. So the slope is negative. So what will be the value at this point we have to find, and what will be the value at this point we have to find. So to find the value of IC, or to find the value of this point or the coordinate of this point, let us put that IC equals to 0 in this circuit equation. So if we put IC equals to 0 in the circuit equation, then we can find the VCE value will be VCC. So the coordinate of this point will be VCC, 0. Similarly, we can find the value of this coordinate also by putting VCE equals to 0 in the circuit equation. In this circuit equation, if the VCE value is 0, then the IC value will be VCC by RC. So we can say that the coordinate of this point will be 0, comma BCC by RC. This is the true coordinate of this point, and this line is referred to as the DC load line of the bipolar junction transistor. This is the DC load line of the bipolar junction transistor. We also know the output characteristics of the bipolar junction transistor connected in the common emitter mode. If we plot the DC load line and the output characteristics, that is IC versus DCE, when IB is constant or fixed. In this plot, if we plot the DC load line also, then it will look like this. As we know that this is the output characteristics of the BJT in CE configuration, and in this plot there are three regions. This is the saturation region where both the junction are forward bias, and this is the cutoff region where both the junction is reverse bias, and in between this where the IC is saturated for the increasing value of VCE, this region is the active region. And if we now plot the DC load line here, then the DC load line will look like this. This is the DC load line, and this value we know that it will be 0, VCC by RC. We have already derived that. Similarly, this value is VCC, 0. This is the DC load line, and we can see that the DC load line has got the output characteristics at different points. These are the points where the DC load line has got the output characteristics, and these points are called the operating points of the transistor. Sometimes they are also called the Q point. This cut point or intersection point are the operating point of the transistor. So there are so many operating points right now. So if I denote, it is the Q1, it is Q2, it is Q3, it is Q4, and it is 5. There are 5 operating points. That means the transistor can now operate on these 5 operating points. Now, out of these 5 operating points, which one of the operating points will be suitable for the BJT to operate? If we consider the operating point as Q1, then for this Q1, we will get a particular value of BCE as well as a value of IB or IC. That is, for this, let us assume for Q1, let us assume we will have a VC1 value, and here we will get a IC value. Similarly, for the Q2, we will get a IC2 value, and the VCE value will be, let us assume that it is VCE. Similarly, for Q3, the VCE value we can get as VCE. Similarly, for the Q4, we can get the VCE value as VCE4, and for Q5, it will be VCE 5. So these are the different collector to emitter voltage that can happen for different operating point. So for Q3 value, I find the IC value, so it will look at IC. Similarly, for the Q4, we can have this IC, and for Q5, we can have the IC value as IC5. So every operating point, that is Q1, will be specified by the value of VCE1 and IC1. Similarly, Q2 will also be specified by particular value of collector to emitter voltage and IC2. Similarly, Q3 will be specified by VC3 and IC3. Similarly, Q4 will be specified by VCE4 and IC4. Similarly, we can say that Q5 operating point will also be specified by VCE5 and IC5. In this way, the every operating point can be denoted. Operating point means some particular value of collector to emitter voltage and IC current. Now, if we want to find which one of the operating points will be the perfect operating point for the transistor to operate, then always the operating point which is which is just at the middle of the characteristics, the operating point which is just at the middle of the characteristics will be best to operate the BJT at. So we can see that the Q3, this Q3 is the operating point which is near at the middle of the characteristics. So this operating point is very suitable to operate the transistor at this point. Otherwise, there will be a clipping of the signal if we operate the transistor in the Q1, Q2 and Q4, and there will be a clip version, there will be a clipping of the input signal and the output. But at the Q3, there will be no clipping of the signal that will be applied at the input. So we will get a full waveform, complete wave that we will apply in the input as the output. That's why Q3 is the perfect operating point that can be used to the transistor to operate. Now we have seen the DC load line. Let us see what will be the AC load line. So if we see the AC load line equation, the AC load line equation looks like this. It will be VCE equals to minus IC into RC. So this is the AC load line equation of the transistor. All the DC voltages has been 0 because we are doing the AC load line, and this AC load line, on this AC load line I can find the value of IC as minus 1 by RC into VCD. both the AC and DC load line will coincide at some point with each other, but the origin of the DC load line, right? The origin of DC load line will be at the 0, 0 point, but the origin of the AC load line will be the Q point. This is the difference between the AC load line and the DC load line. So, what is the importance of this Q point? Suppose let us consider that a transistor operating at Q3 point, and somehow, and if it is operating in the Q3 point, so the value of the VCE will be VCE, and the value of the IC will be IC3. So this is the transistor which is operating at a Q3 point, this Q3 point. So somehow if the temperature increases, then we know that the minority carrier current ICO increases and the IC current also increases. So that's why due to the increment of this temperature, the IC current has been changed. So this IC3 value will be now changed to some other value. So let us say the IC3 has been changed to IC dash, and this IC dash will be greater than IC3 because temperature is increasing. So we can say right now that our IC3 value has been changed to some value IC dash, and this IC dash corresponds to, if this IC dash corresponds to this point, then the corresponding VCE value is VCE. So the operating points has been changed. So the transistor's IC value has been changed. So the operating point has been changed, and it has been shifted from the best operating point to another operating point. So there can be a clipping of the input signal at the output. This must be avoided. And this shifting of the Q point, or we can say that shifting of Q point in transistor operation can be removed or balanced by proper biasing circuit. And in this way, by using the biasing circuit, we can we can stabilize the transistor. That is known as the stability of transistor. So let us see how the biasing circuit will look like. Generally, this is the circuit, that is the biasing circuit we know, because this is our transistor. The circuit connected with these transistors are the biasing circuit. Now in this circuit, we can say that this is our input loop and this will be our output loop. So from the input KVL, if we apply input KVL, then we can find the following equation. It will be minus VBB plus IB into RB plus VBE equals to 0. Similarly, from the output KVL, we find the output KVL equation will be minus VCC plus IC into RC plus VC. So this circuit can be further simplified like this. If we simplify this circuit, the circuit will look like this. There is the BJT, there will be the BJT like this. Is an NPN we have taken. So this is the emitter, this will be the collector, and this is the base. With this, we have connected a RC resistance. There will be an RC resistance here, and with this, we have connected a RB resistance. So we have connected a RB resistance like this. This is the VBB potential that we have applied, and here we have applied the VCC. So this is the RB register, this is the RC register, and here is grounded. And we have taken the output voltage from, if we want to take the output voltage, then we can take the output voltage from the collector. So this is the modified version of the previous circuit. This circuit can be further modified this way, that rather of using the two voltage sources, we can use one voltage source like this. If we have a one voltage source, there is a RB resistance and there is a RC resistance. RC, this is RB. The one voltage source is there, we are naming it as VC. So with RC, there must be the collector, and this is the base, and this is the emitter. The base terminal, and with the base terminal, RB resistor will be connected, and here we will make it up. This is the final circuit we can see. In this circuit, if we assume, let us take some data for our convenience. So let us take that we have applied a 10 volt of VCC, and the value of, if we find the value of RB dash, we can find the value. So if we take the VBE, so this is the voltage across the base to emitter. This is positive, this is negative. This is the voltage across the base to emitter. This base to emitter voltage is here, and let us assume that if we apply the input KVL, then we know from this input KVL equation I can find the value of this RB. If we want to find the value of RB, it will be RB equals to VCC minus E divided by IB. Rather, we can say if we find the value of IB, it will be VCC minus VBE divided by RB. So, if we see the equation of IB here, we can see it is VCC minus VBE by RB, where VCC is constant, RB will also be constant because we have given a fixed value of base resistor, and this VBE value is also near about constant, near about 0.7 volt for the transistor, because it is operating in the active region. So VBE value is 0.7. So we can say from this equation that the base current will also be fixed for this circuit configuration. That's why this circuit arrangement is called the fixed bias circuit. This fixed bias circuit here is called because the IB current is fixed in this equation in this circuit. So now if we find the stability factor of this circuit, we know the IC current is dependent on different stability cases. IC current of the collector current is dependent on the function ICO. It also depends on the beta also, and the IC current is changing with respect to time due to this, with respect to temperature, with respect to the ICO. So we can say the IC depends on ICO and IC depends on beta also. So for the dependency of IC over ICO, we will define a stability factor S as del IC by del ICO. Similarly, we will define another stability factor 1 for del IC by del IB. Del. So the first S factor, that is the stability factor S, denotes how much IC is changing with respect to IC, and S1 denotes how much IC is changing with respect to beta. Ideally, the stability factor value, so the ideal value of the stability factor will be very, if the stability factor value is very small, then it is desirable. That means the stability is very high. Note that since the stability factor value is low, so the stability is high. So low value of stability factor is desirable, and from this circuit we know the stability factor. We have to find the stability factor. So from this circuit we can find the stability factor like this. We know that IC current can be denoted as beta IB plus 1 plus beta into ICO. If we want to find the stability factor S, find del of IC with respect to del of ICO. For that, we have to differentiate this equation with respect to ICO, keeping beta fixed. So differentiating this equation with respect to ICO, keeping beta fixed, we can find the value of S, and it will be 1 plus beta divided by 1 minus beta del IB by del IC. This is the value of stability factor of the. Now, if the beta value is 100, let us consider, take some example, that if the beta value is 100, then we can find the stability factor as 1 plus beta divided by 1 minus beta del IB by del IC, and this del IB by del IC, you can find that this del IB, that is the change of IB with respect to IC in the transistor, is 0 for this operation. So we can say it will be 1 plus beta, that is 1 plus 100, and this is 101. So the stability factor you can see is 101, which is a very high value. That means the stability that we can achieve from the fixed bias circuit is not so good. We have to do something. So for that, what we'll do, we'll go for the meter resistance. So the for improving the stability, we'll go for the fixed bias circuit with RE resistance. Now the circuit will be same, only there will be RE resistance connected at the like this. There will be a connection of RE resistor at this terminal. This is the fixed bias circuit with RE resistance. Now the stability factor, if we find the stability factor going to be 1 plus beta divided by 1 minus, or it will be 1 plus beta into RB, our emitter resistance, divided by plus RB. By derivation we can find this. So this is the stability factor value right now for the fixed bias with emitter resistance. Now if we take some example, so let us assume if the RB value is equals to 930K and the RE value is kilo ohm and the beta value is 100, then we can say if we want to calculate the value of S, then for this condition the S value will be 1 plus 100 divided by 1 plus 100 into kilo ohm divided by 930K plus kilo ohm. After calculation we can see it is 83.15. So we can see the stability factor value has been decreased from 100 to 83.15. So the stability, since the S value has been decreased, so we can say that the stability of the circuit of the circuit is better right now because we want low value of the stability. Now if we go for the further betterment of the stability, then we have to go for the collector to base bias, another type of circuit. So let us move the collector to base bias circuit. So if we go for, now the biasing circuit is collector to base bias circuit. In the collector to base bias circuit, there will be a NPN transistor. So here it will be a NPN transistor. This is the emitter region and this is the emitter, this is the collector and this is the base. Now in the collector to base bias we will connect a VCC here. With that there will be a RC resistor connected here, RC resistor, and the base terminal will be connected to the collector terminal through a RB resistor. So this is the RB resistor and there is a RE resistor connected at the emitter terminal. Basically, the circuit of are collected to base bias using the emitter resistor. In this circuit, we calculate the stability factor like this. Stability factor can also be calculated in a shortcut way like this. Always the stability factor of a biasing circuit can be found like this. In the numerator, it will be 1 plus beta always, and there will be 1 plus beta into, there will be a ratio here, and in this ratio it will be sum, in the numerator part it will be sum of the resistor IC current flows in input loop and sum of the resistor current, sum of the resistor which IB flows in input. So this is the shortcut way by which we can find the stability factor of any biasing circuit. So if I want to find the stability factor from this circuit, it will be as using this formula, it will be 1 plus beta 1 plus beta divided into, now we have to find some of the resistors to which IC current will flow. So IC current will flow in this direction. Okay. There will be IB current flowing in this direction, phase current. So through the RC resistor, there must be the current IC plus IB, because here the IB current, and in the emitter we can say also the IC plus IB current is flowing. Now if we look at the input circuit, our input circuit will look like this. So this is the input circuit that we are considering. In this input circuit, we have to find the resistors through which IC current is flowing. IC current is flowing through the RC resistor and also the RE resistor. So we can say it will be RC plus RE. Similarly, if we find the resistor which the IB current is flowing in the input loop, that is the RB resistor and the RE resistor, and also the RC resistor. So there will be RC plus RB plus RE. Through these three resistors, IB current is flowing, and through these two resistors, IC current is flowing. This will be the value of the stability factor of this connected to base bias circuit using RE resistance. Same thing, the same equation can be also calculated using derivation, but we have used this method. So if I take an example that if my RC value, that is the collector resistance, is 5 kilo ohm and the RE resistor is 2 kilo ohm and the base resistor is 450 kilo ohm and the beta value is 100, then the value of the stability factor will come out to be 39.89. So we can see the stability factor value has been decreased from very high value. Previously it was near about 83.15. Now we have got 39.89. That means the stability of the of the circuit is better now. So to increase the stability of the circuit far better, we need to go another circuit, that is the voltage divider bias circuit. Now the circuit is voltage divider bias circuit. Sometimes it is also called self bias circuit. Using this circuit, the circuit looks like this. There will be a transistor NPN, and there will be a base here. So with this circuit, this is the collector, the emitter, and this is the base terminal, and this is an NPN transistor. Now in this circuit, the circuit looks like this. There will be a RC resistor connected with the collector like this. There will be a RB resistor. There is a VCC source with the base. There will be one R1 resistor. With this base, there will be another R2 resistor that will be grounded. So this is now this emitter is connected to a resistor. This is the self-bias circuit or the voltage divider circuit using the emitter. Here, this circuit can be simplified using this circuit, that there will be the emitter. This is the collector, this is the emitter, and this is the base. This is collector, this is base, and this is. Now with this circuit can be simplified using the Thevenin's theorem like this. This is the VTH and this is the RTH. We can find the VTH and RTH from this circuit, and there was a RC resistance connected earlier. Here it is VCC, this was RC, there was a RD resistance connected here. So this is the RD. Now what will be the value of VTH? VTH value is nothing but the voltage at this terminal, at this point. So we can find the VTH value by the current flowing through the resistor. If we denote the current as I, so I into R2 will be the VTH, I into R. What will be the I current? The same current I is flowing here also. Since the same current I is flowing, we can say that the I value will be VCC divided by R1 plus R2 into. So this will be the VTH value of the VTH can be found from this equation. Similarly, if I find the RTH value, the RTH value will look like this. RTH will be the equivalent resistance at this point. So it is parallel of R1 and R2. That means R1 into R2 divided by R1 plus. Now we have got the value of RTH and VTH. So if we again find the stability factor of this circuit, that stability factor can be found like this way from the previous shortcut formula. So in the numerator it was 1 plus beta, the denominator it was 1 plus beta, and now in the numerator part of this we have to find the resistor, sum of the resistors through which the IB current is flowing. So the IB current that is flowing here in the input circuit, or the IC current is flowing, that is the RC RE here, because here the current is IB, here the current is IC, and here the current is IC plus IE, and the input circuit here is this one. So this is the input circuit. So in this input circuit only the RE resistor is there through which the IB current is flowing. So we can say in the input circuit there is only RE resistor through which the IB current is flowing. So there is a IC resistor, IC current is flowing. So this is the RE. So in the denominator part we can see that we have to find the resistor, sum of the resistor through which the base current is flowing. So one resistor is this one, another resistor is this one, because IB is flowing here, IB is also flowing here. So this is RTH plus RB. So this is the stability equation. Now if we give some example like this, if the R1 is equals to 9K and R2 is equals to 1K and emitter resistance RE equals to 2K and beta is equals to 100, then the RTH value that we can find right now, so the RTH value from this example can say RTH will be R1 into R2 divided by R1 plus R2. If we put the value of R1 and R2, then we can find the value of RTH, and RTH will come out as 0.9 kilo ohm, and the value of the stability factor will be 1 plus 100 divided by 1 plus 100 into K divided by 0.9 K plus. After calculating, we can say it will be 1.44. Right now we can see the stability factor value has been very low. That means the stability of self bias circuit is very good. So this is the voltage divided bias circuit or self bias circuit which has the best stability of the circuit. The stability of this self bias circuit is the best among the three circuits. In this way we can find the stability of a bipolar junction transistor. So this is all about the stability of a bipolar junction transistor. Thank you.